as fxy.
So when we're talking about the
So to solve this differential equation, suppose if we have this as our differential equation, then here you can find your f of xy is x plus y, and your x naught is your
I'm writing psi in terms of
0, and your y naught is your 1. So these are the information given in this
or it is
question.
psi
So we know that the formula for this, calculating the first approximation, second approximation to the solution like this, it is actually this one. Instead of this, I write k, or better to write k plus 1. Then it should be y naught
which one is
plus
one is
integral
symmetry
x naught
as
to
symmetry
x
mode of combination
f of x comma
so so
yk
what if we see the associate
dx.
with
So this is our Picard's method.
constant associated with
So
this factor is become factor number constant coefficients. So it is simple. You can
so we here we have already identified our f of xy is x plus y, x naught is
what happened in this case.
this because the value of y is given at x equals to 0. So whatever is given, we assume this is our x naught, and the corresponding value of y, that is y0, is our
And the second step
y naught. Now we are calculating the first approximation to the solution of this initial value problem. So we know that this is the formula. So if we substitute, what we do, we substitute k equal to 0. If we substitute k equal to 0, here should be y naught, and here we have y1. So y1, so this is actually y naught, it is given here. So this is y naught, x naught to x, 1 plus x dx. Because y naught is 1, so x plus y is 1, so 1 plus x. So you have this one as a y1x. Now this one is y1. So to calculate like y2, you have to substitute this k equal to 1. So here you have to calculate yx y f of x y1. So to calculate f of x y1, because f of x y is defined as this one, so it will be x plus y1 if you are calculating f of x y1. And what is the value of y1? Value of y1 is this one. So 1 plus x plus x square by 2 plus x. So after this, after substituting, you will get this thing. Actually, they have missed this 2 here. Like if we add this x to this x, it will get 2x. So 1 plus 2x plus x square by 2. And then it is a second approximation. Here is also 2. So y2 is equals to y naught plus x naught to x, 1 plus 2x plus x square by 2. So the integration of 1 is x, and the integration of 2x is x square by 2. So this 2 will be cancelled out. You have x square, and then we have x cube upon 6. So this one, these terms are there. But when you substitute the lower limit and upper limit, this is the lower limit and upper limit is x. Not in this actually. The integration is different. Actually, this is totally simplified one. The integration is like x plus x square plus
So this is the bonding.
x6
So due to
over,
this, so if
sorry,
the question maybe get question will come that
x
draw
3 over 6.
symmetries or bonding states.
And then you substitute
What is how the UA functions
1 to
looks like.
x.
So you have to remember.
So if you substitute 1 to x,
So this will be all as positive. Okay.
then you will get like
Symmetry.
for substituting x, you will get x plus x square by 2 plus x cube by 6. For 1 you will get 1 plus 1 plus and 1 by 6.
So
Then
one is
they are
okay.
having this.
So the electron distribution function, you can see that how it looks like. But when you find out the
This is
energy,
pi
I have
plus
already
x.
told you that when you find out the energy, the asymmetric states,
I think they have
asymmetric state
done
will
something
be higher energy. Okay, that is
wrong.
also called anti-bonding states.
Okay,
So,
sorry.
anti-bonding states.
Actually, this x naught is 0. So the lower limit is 0 here and upper limit is x. So when you substitute x, you will get these terms, these x square and x cube by 6. And when you substitute x equals to 0, you will get 0. And this one is from this side. So you have this as your y2. Now to calculate y3, again you have to use your formula. This is y naught plus x naught to x 1 plus this. This is our actually. This is our actually fxy2. This is fx because we require this one now. Fxy2. So y2, if you substitute, because value of y2 is this one. So again they have missed one 2 here. It should be 2x. And then after integration you will get these results. So like this we do in every steps, and we will get like up to fifth of approximation. So here this solution, like this one is a better approximation to the solution. Y4, Y5 is a better approximate solution to Y4 to the given differential equation. So this is the way our Picard approximation method works. Then we have, suppose you have this kind of equation. So here again you have to assume like this. Y minus this thing is our fx y. Actually this is y minus x upon y plus x, and then you have to identify. So x naught is your 0 and y naught is your 1. So your like this is y naught and this is f of xy initially. So you have substituted like this. So and then you have to integrate it. So to integrate it, like we have to rearrange these things in like this, and then thereafter we integrate, we will get this as y1. Like after integration and substituting the limit 0 to x, you will get this. Similarly, now you put y, this one in here, wherever is y is there, now you have to substitute, because this one is actually y naught, you have, and y naught is actually 1, so you have done this thing, and then now y1 you have to substitute. Actually, they have, this is y naught, so 1 we have to take everywhere, wherever is y. So like minus 1 plus 2 upon 1 plus x. This y is actually 1. We are substituting in this f of xy. Initially we required this f of y naught, that is actually f of x1. So wherever is y is there, we have to replace y by 1 and then simplify, we will get this. So this is now our y1. Now wherever is y1, like wherever is y, we have to replace that y by y1 to get the next approximation. So you can see that this is y now replaced by y1, and then you simplify it and integrate. So like it's difficult to integrate, so they left here So then they have assumed that this one is the first approximation is the solution to the differential equation, and then they have, because it is a solution of y1x, it's a function of x, and now they are desiring the value at the x equals to zero point 0.1. So you substitute x equals to zero point 0.1 in this solution, you will get the value of y at zero point 0.1 from this equation like they are calculating here. Then we have another method known as Taylor series method. Again, we have the differential first order linear differential equation. So if we differentiate this equation, we will get d2y over dx2, and here is a function of two variable x and y is again a function of x. So if you are differentiating this, so then you apply total differentiation rule. So you will get del f over del x and then dx over dx. So dx over dx is 1, so that term is not here. Plus del f over del y dy by dx. Because y is a function of x, so we have this way. So the differentiation of f of x y with respect to x will give us this. And then del f over del x you have represented by this f suffix x, and del f over y by f suffix y, and dy by dx as f dash. Instead of f dash, they have to write f only actually, because this is dy by dx, and dy by dx actually this one f of x y. So this f is wrong here. So, like, did we can calculate like a second and third order differentiation of from this equation, like d3y over dx3 can be calculated, and d4y over dx4 is also calculated from this equation 1. And then we know that the Taylor series expansion of y about the point x, because here y is a function of x, and we are expanding this y function about the point x naught, or we say in powers of x minus x naught. So if we are doing this, then the value of y naught, x minus x naught, y dash naught, x minus, this is the Taylor series expansion of the function y about the point x equals to x naught. Then like this is the like we actually terminate this Taylor series expansion. If we terminate here, then we say it's a second order method, and if we terminate here, then we say it's a first order method. So depending on this, the number of terms we are considering in the Taylor series method, different methods of different orders will be generated. So, so like suppose we have this one. So y dash is equals to this one, and then we apply Taylor series method. So we know that this is the Taylor series expansion of y about the point x naught, and then we have to calculate this because here y dash is required, y double dash is required, and y triple dash is required. Y dash is given to you. This is actually dy by dx, and then you have to calculate y double dash. So it means you are differentiating this with respect to x. You will get y double dash. Differentiation of x is 1, and differentiation of y is y dash. And then you have to calculate y double dash 0 because it is required here. So y double dash 0 is equal to here 1 plus y dash 0. But what is the value of y dash 0? So we calculate from here. It is like y dash 0 is like 0 plus value of y at 0, because wherever x we have to substitute 0. So what is the value of y0 given to us? The value of y0 is given to us here as 1. So it should be 1. So y dash 0 is 1. Now you substitute the value of y dash 0 here. You will get 1 plus 1 equals to 2. So this is the value of y double dash 0. Similarly, you can calculate y triple dash 0. So triple dash 0 means I have, because if I differentiate this one more times I will get this. So it means if I try to calculate at 0, so it means y triple dash at 0 equals to y double dash at 0, and the value of y double dash 0 is 2. So the next all derivatives are equals to 2. Then we substitute in the Taylor series. So if we substitute all these values, we will get this. X naught is 0, as this is initial point. X naught is 0. So x naught is 0 here. So y naught plus x minus x naught y dash naught x minus x square upon 2 factorial y double dash naught. So here we substitute all these values of y dash naught, y double dash naught, y naught, and we will have this. And so like we know that we are not going to calculate all the infinite terms. So somewhere we have to truncate. So like if we are considering the terms up to here, then we have this as a value to this. Similarly, like if we want to know what is the value of y 0.2, then you have this one. You have substituted x equals to 0.2. This is the solution yx, and you substituted once x equals to 0.1 to calculate this thing, and then you have substituted x equals to 0.2 calculate this thing. So this is the way our Taylor series method will work.
Question will come. What is the importance of antibody states? आपको तो पता चल गया कि linear combination हुआ plus and one plus state one.
Okay, then we have this Euler's method.
That is the important antibody state.
So this is we have
And
already
what is
discussed
the
these things.
antibody states? The linear combination of psi one plus psi two or phi a, whatever psi or phi, whatever you say. So it is phi a plus phi b, and one is phi a minus phi b. But my phi a minus
So
phi
like
b is higher
if
than
you
phi.
are, this is the like a Taylor series method again.
What is the
So if
significance
you
of
are
this
considering up to like h raised to power p terms and neglecting other terms, like this is the remainder form of the Taylor's term, Taylor series. So this is like plus this one, like so if you are restricting yourself up to h raised to power p, then your method is known as Taylor series method of order p. So if you restricted up to two, up to if you consider only that many terms, then your method is known as Taylor series method of order 2. So like for different values of p, we can have different method. Like for p equal to 1, so it means we are considering up to here h raised to power 1 only. So y I plus h, here h is your x minus x naught, and y dash of I you can say dy by dx at x equal to xi, and y of I plus 1, that means y of xi plus 1. It means earlier we have x naught, instead of x naught we are taking the point xi as the initial point, and we are calculating the value or the solution at xi plus 1 point. So the x naught is replaced by here xi actually, and x1 is replaced by xi plus 1. So if we take only p equal to 1, then it is known as the Taylor series method of order 1. Then if you take two terms, then it is known as the Taylor series method of order 2, and similarly of order p. Then
Antibodies. Clear? So one is considered as the
so suppose you have this initial value problem, this y dash equals to x. So this is your problem, and then y naught of 0. Actually, they have discussed the Euler's method earlier. Actually, this Taylor's first order method is also named as Euler's method. This one. So sometimes, like instead of writing Taylor's first order method,
Valence band and convection forms.
This is Taylor's first order method, and this is most useful actually. When we go for further methods, this is the basic step of those methods.
Actual material.
So this one is actually sometimes is known as Euler's method or Taylor's methods for first order. But most of the times, authors when they say that you have to solve this method by Euler's method, you have to apply this method. So Taylor first order Taylor series method is actually Euler's method, and it is like this: you are calculating y at xi plus 1 point is equals to y at xi plus h y dy by dx at xi, and what is h? H is the difference between xi plus 1 minus h is equals to xi plus 1 minus xi, and this is the general form like this. Instead of remembering this in terms of I dash, we remember this in this form because y dash dy by dx is actually f of xy. So this is like most
What is one is
yi plus 1
computer.
equals to yi plus h f of xi
Only one electron is
yi. So this is actually the most general form of Euler's method. When we apply somewhere, we remember this one because yi dash actually equals to f of xy. So if we calculate f of xy at the point xi, we will get f of xi yi. So we apply this method to solve this problem. So we have this initial value problems, and we have to apply Euler's method, and we have to find the solution from x equals to 0 to x equals to 0.8, and with the common step like 0.2. So it means we have to calculate the solution at x equals to 0.2, x equals to 0.4, x equals to 0.6, and then x equals to 0.8. And like if we take this as an h, or if we take this as an h, then we have to calculate the solution at x equals to 0.1, 0.2, 0.3, 0.4, and up to 0.8. And then we have to actually compare the result with the exact solution. So we'll try to find its exact solution, and then we compare the result of exact solution with these two numerical solutions. So first we write what is our y dash. So if I simplify this, I will get x upon y like this. Because if I divide from this y, I will get x upon y. So whatever is dy by dx, it is actually known as f of xy, fx comma y, and this is actually the definition of f of xy now is x upon y. Now the Euler's method is y at xi plus 1 is equals to y at xi plus h f of xi yi. So what is the definition of f of xi yi is here? This one, x upon y. So we replace x and y by x by xi, y by yi. So we'll have this one, yi plus h xi upon yi. Now the initial value is given here, this one. So here x naught is 0 and y naught is 1. So because of this initial condition. So x naught is 0, y naught is 1. So y at xi plus 1 is equals to yi plus h. So initially, like first we are solving taking this as a step size, or we actually have to calculate the solution at the interval of difference 0.2. So if we are taking h equals to 0.2, so we have to substitute the value of h here, and the value of h is 0.2, and then xi and yi. So in particular, like when you substitute I equal to 0 here, if you substitute I equal to 0 here, you will get y at x1. Actually this is y1. Y at x1 is equals to y at x
electronic state के bonding करके इसे balance point condition में थोड़े
So
semiconductor
actually x1 is 0.2, so
no
they have substituted the value of x1 as 0.2. Actually
yes or
this is
no
x naught is here actually, sorry,
कब
x
तक
naught
ये
is
है
here 0,
exactly the maybe
h is
the
your
I don't know
0.2,
or not I
then
believe that
x1 is your like
PhD स्टूडेंट के साथ
x naught
बात करके
plus
आपके साथ बात करके
h
कंप्लीट हो गया तो आपको
is 0.2. Then similarly like you can calculate x2 also, because x2 is like x1 plus h, then it is 0.4. So y of x1 we are calculating here, and this is y at 0.2, and then we use this formula on the right side. It is actually y at naught, so y at naught actually y at 0 plus 0.2 x naught upon y naught. So y naught is 1, so it is like 1 plus 0.2, x naught is actually 0 divided by 1. So finally this term is 0 and you have 1 in this solution. So y of x1 is this one. Now to calculate y at x2, so x2 is our 0.4, so y at 0.4, and then we use this right side formula. So this is actually now I is actually 1, so y1 plus 0.2 x1 upon y1. So y1 is 1 we have obtained from previous step, and 0.2 as it is. Now x1 is your 0.2 again, and this y1 is 1 we have obtained, and after simplification this is 1.04 as the value of yx2. Similarly, to calculate yx3, since x1 is 0.2, x2 is 0.4, so you know that x3 is 0.6. So y of x3 is equals to this one, and then this is actually y3, but the formula on the right side, if we replace I by 2, you will get this y2 plus 0.2 x2 upon y2. Y2 you have obtained in the previous step, so you have substituted here 1.04, then 0.2 x2 is 0.4 divided by y2, and after simplification you have this. Similarly, you can have the value of y at x4, that is y at 0.4. So you will get this value. So when we have solved this using h equals to 0.2, so this is the solution of the differential equation. So like when we are solving this equation in using our analytical method, we have solution in terms of the function of yx, and we use or we can substitute any value of x and you will get the value of y. But here in like when we have this iterative steps methods, you are able to find the value at that discrete points, like you know the value of y at 0.2, y at 0.4, y at 0.6, not other than those points through these iterative method. Now if you want to know the more values of y, so you can reduce your step size h from 0.2 to 0.1, so you will get more values or more solution values of y. So like if I take h equals to 0.1, so yi plus 1 equals to yi plus h f of xi comma yi. F of xi comma yi is xi upon yi for this particular problem, and h is 0.1. So now what is x1? Earlier h is like 0.2, but now h is 0.1. So this is your 0.1. Similarly, your x2 is like a 0.1.
So these two states find out, and I have already told you one is
0.1 plus 0.1, and like 0.2, and in general it's like x3 is 0.3 for this particular problem. So we do the same thing, y of x1, y of 0.1 we are calculating, but we are calculating with the help of our Euler's method. So y1 is equals to y naught plus 0.1 x naught upon y naught. So y naught is given here 1, and x naught is 0. So after simplification, it is like 1 plus 0, finally 1. This is y1. Now y at x2, that is, we are trying to find the value of y at 0.2, but through the Euler's formula, this expression is this one. You have substituted the value of y1, and then you have substituted the value of x1 and the value of y1, and after this you have this one. So similarly, you have obtained the value of y at all these values or points of x. So now you have more values of y within the domain 0 to h as compared to the previous case. Like in the previous case, we know only these four values, but now we have these eight values. So like if you want to know more values of y, then you take like h equals to like 0.0001 and create some program in some programming language, and then you find the most of the value of y so that you can have the solution of y at more number of points. Now this is the exact solution. Like if we use our analytical method, so we will get this as the exact solution. So we will calculate the value of x at 0.8 using the exact solution. So using the exact solution, we are getting this is the value, and using our approximate solution. So when we have taken h equals to 0.1, this is the solution of y 0.8. So we are calculating the difference. This is exact, and this is approximated. We have taken from here, and then this is the difference. So you can see that when you take less value of h, you will have the less error. More value of h, you will have more error in the solution.
So one is plus,
And then we have another problem, like we have to solve this equation y dash equals to x plus y plus 1 with this y equal to 0.2 as the initial condition, and we have to calculate y at 0.2 with h as a 0.1. So and here we have to apply Euler's method and Taylor series method of order 2. So order 2 means we take the h raised to power 2 term, or we consider the term of h raised to power 2 in our method and neglect the other terms other than 2. So up to 2 actually we will consider. So this is the way we will do. Then we have
a few moments, a few seconds. It's 10 to the power minus 12.
Lavisha, is there problem with your mic?
And it will jump from antibody exchange to body.
Lavisha?
Okay. So initially, if the energy absorbed by the electrons occupied in bonding states, then it will be excited.
So
it will go to the antibody states with.
So we have to solve this initial value problem. So first our job is to identify what is f of xy. So you can see f of xy is here our y dash, and this one is your x plus iy. Sorry, x plus y plus 1, and then the identity you have to identify x naught. So x naught is this actually. So this is 0. And y naught, y value of y at 0, this is y naught. So this is the thing you have to identify from your given problem. What is f of xy, what is x naught, and what is y naught. Now you have to first you are applying this Euler's method. So to apply this, you take this is the form of the Euler's method, and then you have yi plus 0.1, and then actually they have missed the Okay, they have actually directly substituted the value of x equal to xi and y equal to yi here. So you have this one. Now you have to, so because they are telling that you have to take h equals to 0.1. So to take h equals to 0.1, it means I have to apply two times this Euler method. Then only I will able to reach this y equals to 0.2. So x naught is 0, y naught is 1. So the value of y at 0.1 is like y naught plus 0.1, x naught plus y naught plus 1. So x naught is 0, y naught is 1. As x naught is 0, this part is 0. So this is y of 0.1. Then I calculate y at 0.2, that is y2, and y2 is y1 plus 0.1, x1, y1 plus x1. So x1 is 0 plus 0.1 because 0.1 is h. So x naught plus h is this one, and y1 we have obtained from here. So and then y2 by using our Euler's formula, and this is 1.0.2. Now we have to apply this Taylor series second order method. So that is we are considering the terms in the Taylor series up to order or up to power of h raised to power 2. So if we considering up to h raised to power 2 and neglecting other terms, so we will get this one. So here, like y dash is actually always given to us in our problem. Like this is f of x y, but y dash but in this Taylor series second order method, you required y double dash also. So it means you have to differentiate your differential equation with respect to x one time. So this is your dy by dx, and you differentiate this one time with respect to x, you will get y double dash x equals to this first function x as it is, and the differentiation of y plus 1 is y dash. Then second function as it is, and the differentiation of x is 1. So this is the differentiation of one time differentiation of the given differential equation. So this is the value of y double dash. So you substitute this value of y double dash here. So now we are calculating this. What is the x naught? This is given. Y naught is given because y dash of naught is also required, because when we substitute I equals to 0, then we will get y1. So here we required y naught of dash, and here we required y naught double dash. So what is y naught dash 0? So y naught dash, actually this is your dy by dx, and in this case it is like x into y plus 1. So if you substitute x equals to 0, because this is your y dash, if you substitute x equals to 0, you will get 0. So y dash of 0 or x naught is 0. Now y to calculate y double dash at 0. To calculate y double dash at 0, you have to substitute here x naught y naught dash plus y naught, because it is now the function of x, so yx. So when you are talking about y double dash of x naught, it is like x naught y dash at x naught and y at x naught. And y at x naught is represented here as y naught, and y dash of x naught is represented at this. So y dash of x naught is already calculated here. This one is 0. But y at x naught is given to us. This one is 1. And this one is in the form of y double dash. So 1 plus 1, you are getting 2. So now you have y naught double dash. Now in this Taylor series second order method, what you do, you put I equal to 0. So if you substitute I equal to 0, you will get y1 equals to y naught plus 0.1 y dash plus 0.005 y double dash naught. And then you substitute all the values. Y naught dash is 0, but y naught double dash is 2. So after simplification, this is the value of y 0.1. Then to calculate at x1, so if to calculate at x2, so I have to substitute here I equal to 1. So if I substitute here I equal to 1, it means I required y1 dash and y1 double dash. So what is y1 dash? So if I calculate y1 dash, it means it is x1 and y1 plus 1. So to calculate this y1 dash, because the definition of y dash is this one, and now I have to calculate this dy by dx at x equal to x1, and x1 is 0 0.1, so 0 0.1, then y1 is 1.01, that is calculated in previous step. So we have substituted and we have this one. Now y1 dash we have. Now we calculate y double dash at x equal to x1. So this is the form of y double dash x. So here I have to substitute everywhere x equal to x1. So x1 y1 dash plus y1 here means y at x1 plus 1. So y1 dash, it is actually calculated here 0.201, x1 is 0.1 from here, and y1 is from the previous step, and the 1 is in the definition of y double dash x. So after simplification you have y1 double dash. Now you have y1 double dash and y1 dash also. So then you can substitute here in this formula. In this formula you substitute I equal to 1, you will get this y2 equals to y1 plus 0 0.1 y1 dash plus 0.005 y1 double dash, actually y1 double dash. So y1 is 1.01, that is from previous step, then 0 0.1 y1 dash is this one, that is calculated here, and y1 dash is double dash is this one, that is calculated here, and after simplification this is the value. So similarly you can have Taylor series fourth order method also. Here you have to consider the terms up to power h raised to power 4 and neglect others, and in the similar way you can do all this calculation. So here you earlier you have to calculate y I double dash, now you have to calculate third derivative and fourth derivative also. So they have calculated here. This is the second derivative. If I differentiate it one more time, I will get third derivative, and if I differentiate this, I will get the fourth derivative. And then, as we calculated for second order method, similar way we will calculate for fourth order method also. So then we have this Euler's modified method. So this we will discuss in the next class. And then this Runge-Kutta method. There are two, some methods are also there. I don't know. Okay, they are there actually. Okay. Okay, we'll discuss this in the next class. Then so now I take the attendance. Abhijit, are you trying to say anything?